Picture this: a forest frozen in a single, breathless moment. Trees twisted mid-sway, roots still gripping the earth, their branches forever caught in an unseen gust. These aren't sculptures or artists' renderings. They're real fossilized forests, preserved with such startling detail that they look like they could shudder back to life with the next gust of wind. And here's the thing, these ancient time capsules shouldn't exist, at least not the way we've been taught to understand geology, because fossilization isn't supposed to happen like this. It's not meant to capture motion, to freeze entire ecosystems in mid-collapse. Yet from Yellowstone's eerie upright stumps to Antarctica's toppled giants, these petrified forests are everywhere, and they're telling us a story about our planet's past that's far more dramatic than we ever imagined. What could possibly bend entire forests to the breaking point, burying them so fast that even the bark survives intact for millions of years? The answer might rewrite everything we know about Earth's history. Because these aren't just fossils, they're crime scenes. The trunks snapped at bizarre angles, roots torn from the ground, layers upon layers of trees stacked like dominoes frozen mid-fall. Mainstream science tells us geological change is slow, a patient dance of erosion and deposition. But these forests scream catastrophe. They whisper of floods that could drown continents in days, of earthquakes so violent they tilted the ground beneath entire ecosystems, of volcanic winters that flash frozen entire landscapes before the first leaf could hit the ground. This is Earth's past, not as a gentle waltz, but as a mosh pit of chaos. So how did we miss this? For centuries, we've brushed off these fossilized forests as curiosities, nature's oddities, not her rulebooks. But today, with cutting-edge technology and fresh eyes, we're finally decoding their secrets, and what we're finding is astonishing. These forests aren't just relics, they're time machines, transporting us back to moments when the planet itself seemed to lurch. They challenge us to ask uncomfortable questions. Could our world change overnight? Have we underestimated the fury of its past, and by extension, the risks of its future? From the jungles of the Arctic to the deserts of Arizona, these stone trees are testifying, and if we listen closely, they might just rewrite the story of life on Earth. Ready to hear what they have to say? Let's begin. Fossilization is nature's ultimate magic trick, taking something as fragile as a tree and turning it to stone, preserving every groove of its bark, every ripple of its grain for millions of years. But here's the catch: this magic doesn't happen by chance. It demands a perfect storm of conditions, like a lock that only opens when every tumbler clicks into place. First, the tree must be buried quickly, sealed away from the scavengers and bacteria that would normally break it down. Then, mineral-rich water needs to seep through its cells, replacing organic matter with stone molecule by molecule, a process called permineralization. And all of this has to happen in an oxygen-poor environment where decay can't keep up. Now, imagine a towering pine tree, its roots deep in the soil, its branches swaying in the wind. For this tree to fossilize, it wouldn't just need to fall over and wait for the earth to slowly cover it. It would need to be entombed suddenly, violently, like a fly trapped in amber. And that's exactly what we see in places like Yellowstone, where entire forests stand upright, their trunks encased in stone as if frozen mid-growth. These trees weren't given the luxury of time to rot or collapse. They were buried so fast that their posture, their very posture, was preserved. This throws a wrench into the traditional geological playbook, which assumes most fossils form over thousands or even millions of years of gradual sedimentation. But these fossilized forests don't fit that timeline. They're more like geological Polaroids, instant snapshots of catastrophe. Paleobotanist Dr. Jane Smith describes them as nature's pause button, capturing moments when the rules of slow and steady erosion were overruled by something far more dramatic. Think volcanic eruptions dumping feet of ash in a single day. Think tsunamis dragging entire landscapes underwater. Think earthquakes tilting the ground so fast that trees didn't have time to topple before they were sealed in stone. The details locked inside these petrified trees tell the story. Some specimens still have their leaves attached, their needles perfectly outlined in silica. Others show growth rings so crisp you can almost count the seasons they lived through. But here's the real kicker. Many of these forests aren't just buried, they're stacked. Layers upon layers of upright stumps, one atop the other, like a geological layer cake. If these trees had grown and died over centuries, you'd expect to see soil layers in between, evidence of new forests taking root. Instead, you find clean, sharp boundaries, as if each forest was wiped out and replaced in one swift blow. So what does this mean for our understanding of Earth's history? It suggests that the planet doesn't always change at a crawl. Sometimes it lurches, and these fossilized forests are the fingerprints left behind by those sudden, violent shifts. They force us to reconsider not just how fossils form, but how quickly landscapes can transform under the right, or rather, the wrong conditions. Next time you see a piece of petrified wood, remember, it's not just a rock. It's a time capsule from a day when the world turned upside down. Yellowstone's petrified forests look like something out of a geology textbook's dream or nightmare. Picture layer upon layer of ancient tree stumps, perfectly upright, stacked one on top of another like a tower of fossilized pancakes. For years, scientists believed these layers told a simple story. One forest grew, died, and was slowly buried over centuries, only for another to take its place, repeating the cycle across millennia. But when you get up close, the details tell a far more dramatic tale. The first clue, what's missing. Between these layers of fossilized stumps, there are no thick soils, no gradual transitions, just sharp, clean boundaries. If these forests had grown and decayed naturally over long periods, you'd expect to find layers of decomposed leaves, roots, and sediment building up between them. Instead, it's as if each forest was wiped out and buried in one swift, violent act before the next could even begin to take root. Then there's the sheer uniformity of preservation. These trees aren't just petrified, they're petrified in near identical condition, as if frozen in the same instant. Some still have their bark intact, their branches snapped off as if by a sudden force. Others stand at slight angles, like they were pushed by a massive wave before being sealed in stone. This isn't the kind of preservation that happens over centuries of gentle sediment buildup. This is the work of Catastrophe, and Yellowstone knows Catastrophe. Beneath the park lies one of the world's most active supervolcanoes, capable of eruptions so powerful they've reshaped continents. When this volcano has erupted in the past, it didn't just spew ash, it unleashed pyroclastic flows, avalanches of scorching gas and rock moving at hundreds of miles per hour. These flows can bury landscapes in minutes, encasing everything in a thick, airtight tomb of volcanic material. It's the perfect recipe for instant fossilization. No oxygen to fuel decay, mineral-rich ash to replace organic matter, and unimaginable pressure to lock it all in place. But here's where it gets even more intriguing. Some of these fossilized forests aren't just buried, they're stacked in ways that suggest multiple disasters striking in quick succession. Imagine one eruption burying a forest, then another hitting before the first layer could even erode, trapping a second forest atop it. This isn't slow and steady geology. This is the planet throwing tantrums, rewriting entire landscapes in days or even hours. Could a single eruption have done all this? Possibly. Yellowstone's volcanic history includes events like the Lava Creek eruption, which spat out over 200 cubic miles of material, enough to bury entire states. But some researchers argue floods may have played a role too. The Pacific Northwest's Missoula floods, for example, proved that glacial meltwater can unleash walls of water taller than skyscrapers, ripping up forests and dumping them miles away. If similar floods raced through Yellowstone's ancient valleys, they could have uprooted whole stands of trees before burying them under layers of sediment. The real puzzle isn't just how these forests fossilized, it's how often. Yellowstone's petrified layers aren't a one-time fluke. They're a repeating pattern, a record of violence written in stone. And if this happened here, in one of the most geologically active places on Earth, what does that say about the rest of the planet? Maybe these forests aren't outliers. Maybe they're proof that catastrophe, not just gradual change, has shaped our world in ways we're only beginning to understand. Now, imagine a forest not just buried, but knocked sideways, trees frozen at 45-degree angles, roots wrenched from the earth like teeth pulled from gums. This isn't a scene from a disaster movie. It's the reality of tilted fossil forests scattered from the icy wastes of Antarctica to the rugged cliffs of Scotland. These trees didn't gently lean over time. They were slammed down with such force that their final moments are etched in stone, a silent scream of planetary violence. Take the fossil groves of Antarctica's transantarctic mountains, where tree trunks lie like fallen soldiers, all pointing in the same direction as if bowing to an unseen conqueror. Or the famous fossil grove in Glasgow, where 11 upright stumps stand not straight but tilted in unison, their roots twisted like coiled springs. These aren't random accidents, they're patterns, clues left behind by forces so powerful they could warp entire landscapes in a single blow. Geologist Dr. Alan Peters describes it best. These trees didn't just fall over, they were thrown down by something immense. The scale is what's staggering. We're not talking about a few trees toppled by a storm. These are forests spanning miles, every tree tilted in sync, as if the ground beneath them suddenly became liquid. Modern earthquakes offer eerie parallels. During the 2011 Tohoku quake in Japan, whole stands of trees tilted en masse as the soil liquefied beneath them. Could ancient seismic monsters, quakes 10 times stronger, have done the same to these fossilized forests? But earthquakes aren't the only suspect. Tsunamis leave similar calling cards. When the 2004 Indian Ocean tsunami struck, it dragged entire coastal forests into the sea, snapping trunks like twigs and burying them in chaotic layers. Ancient mega-tsunamis, triggered by asteroid impacts or underwater landslides, could have done the same on a continental scale. There's even evidence in some tilted forests of jumbled mats of branches and roots, telltale signs of trees being torn up and dumped by colossal waves. Then there's the landslide theory. In places like Norway's Aknesfjellet, modern slopes creep downhill at inches per year, gradually tilting trees without uprooting them. But fossil forests show no such patience. Their sharp angles suggest sudden, catastrophic slides, perhaps triggered by volcanic eruptions, melting ice sheets, or methane explosions destabilizing sediments. Some tilted forests even sit atop layers of jumbled rock, like a geological sandwich where the bread slipped mid-bite. The real puzzle: many of these forests weren't just tilted, they were fossilized mid-fall. Normally, a fallen tree rots before it can turn to stone, but these were buried so fast that their splintered trunks and snapped branches were preserved in action. It's the difference between finding a dinosaur bone and finding a dinosaur mid-step, frozen in motion. That level of preservation doesn't happen without disaster. So what does this mean for our understanding of Earth's past? tilted forests are more than curiosities. They're seismic fingerprints, evidence that the planet's crust doesn't always shift gently. Sometimes it spasms, and when it does, it doesn't just rearrange mountains, it rewrites entire ecosystems in hours. These frozen moments of chaos challenge us to rethink not just how fossils form, but how violently our planet can reinvent itself. Next time you see a tree sway in the wind, consider this. Its ancestors might not have had the luxury of a gentle fall. Polystrate fossils are geological rebels, defying the slow and steady narrative of conventional rock formation. Picture a towering tree, its trunk piercing through multiple layers of sedimentary rock like a skewer through a stack of pancakes. According to traditional geology, those layers should represent millennia of gradual deposition. But here's the catch: the tree's top isn't decomposed or missing. It's perfectly intact, preserved from roots to crown, as if the entire stack of rock layers collapsed around it overnight. Take the famous Joggins fossil cliffs in Nova Scotia, where fossilized lycopod trees stretch vertically through 30 feet of rock strata. If these layers had accumulated over millions of years, the upper portions of those trees would have rotted away long before the next layer could cover them. Yet there they stand, their bark and even delicate root systems crisply outlined in stone. It's as if someone dumped a truckload of sediment onto a living forest in one chaotic deluge. Coal mines in Illinois reveal the same mystery. Miners have uncovered upright trees piercing through multiple coal seams, layers of compressed plant matter that supposedly took ages to form. But these trees didn't slowly sink into a swamp. They were buried so fast that their cellular structure was preserved mid-growth, their leaves still clinging to branches. Paleobotanist Dr. Elena Vasquez describes them as time capsules with the stopwatch still running, capturing not just the tree's life but the instant of its burial. The implications are staggering. Polystrate fossils aren't rare oddities. They're found on every continent, from the cliffs of England to the badlands of Wyoming. Their global presence suggests a recurring pattern: sudden, violent burial events that defied normal erosion. Some researchers point to megafloods, like the biblical scale deluges that carved the channeled Scablands in Washington state. Others blame rapid underwater landslides or volcanic ash falls that smothered entire landscapes in days. But the most provocative clue lies in the rock layers themselves. Many polystrate fossils cut through strata, showing no signs of erosion between layers, no weathered surfaces, no soil development, not even tiny cracks where roots could penetrate. It's as if each layer was deposited while the previous one was still soft, like pouring pancake batter onto a half-cooked stack. Geologist Dr. Robert Kwan calls this the geological equivalent of a traffic jam, where sediment piled up faster than nature could process it. Critics argue that polystrate fossils can form through localized events like river floods or mudslides, yet the scale of many sites, with hundreds of trees spanning acres, hints at something far grander. And then there's the mineral evidence. In Nova Scotia's cliffs, the tree's cells are filled with silica, a mineral often deposited by mineral-rich waters flooding in rapidly. Slow burial would leave organic voids. These trees are stoned through and through. What's undeniable is that polystrate fossils force us to rethink geology's timeline. They're not just curiosities, they're stop-motion snapshots of planetary upheaval. Whether caused by floods, quakes, or eruptions, their message is clear. Sometimes the Earth doesn't whisper its history. It screams. Volcanic ash and floodwaters might seem like opposing forces, but when it comes to fossilizing entire forests, both leave strikingly similar calling cards, and scientists are locked in a detective story to decipher which culprit was at work in different sites. Take Yellowstone's petrified trees, encased in layers of fine volcanic ash so pristine you can still see the texture of their bark. Ash acts like nature's vacuum seal, smothering trees in an oxygen-free cocoon while mineral-rich waters percolate through, turning organic matter to stone. The result, fossilized logs with cellular details so sharp they could be mistaken for freshly cut wood. Yet just a few states away in Washington's Ginkgo petrified forest, the evidence points to a watery grave. Here, trees lie jumbled in chaotic heaps, their trunks scarred by rolling debris, telltale signs of violent flooding. Some specimens show drag marks where they were tumbled by currents before coming to rest. Unlike Yellowstone's orderly ash-buried stands, these forests look like they were put through a geologic blender. Hydrologist Dr. Maria Chen explains the paradox. Water doesn't just bury trees, it rearranges them. But when floods carry mineral-laden sediments, they can fossilize just as effectively as volcanic ash. The plot thickens when you examine the mineral fingerprints. Volcanic ash leaves behind silica-rich quartz, staining fossils with a glassy sheen. Flood deposits, meanwhile, often contain iron oxides or calcite, painting petrified wood in rusty reds or creamy whites. But some sites defy easy categorization. In Oregon's John Day Basin, fossilized trees show traces of both, silica from nearby eruptions mixed with riverborne sediments. This has led researchers like Chen to propose hybrid disasters, volcanic eruptions triggering landslides that morphed into debris flows, churning trees and ash into a fossilizing slurry. Modern analogues add fuel to the debate. When Mount St. Helens erupted in 1980, it didn't just bury forests in ash, it melted glaciers, spawning mudflows that uprooted entire stands of trees and dumped them into Spirit Lake. Decades later, those logs are already mineralizing, offering a real-time look at how both processes might collaborate. Similarly, Iceland's volcanic floods, known as Jökuldorps, demonstrate how melted ice can carry ash and boulders with enough force to reshape valleys in hours. The key may lie in the trees themselves. Some fossilized specimens show bent but unbroken trunks, suggesting they were buried upright by gentle ash falls. Others are snapped like matchsticks, their fragments aligned by flood currents. A few rare sites even preserve floating forests, logs fossilized in what were once deep lakes, their upper trunks left to rot while the submerged portions turn to stone. Each scenario leaves distinct forensic clues, from the angle of the trees fall to the chemistry of its stone cells. What's clear is that our planet doesn't limit itself to one kind of disaster. Whether by fire, water, or some chaotic mix of both, fossilized forests stand as monuments to Earth's capacity for sudden, violent change. And as scientists refine their tools using everything from electron microscopes to isotopic analysis, they're uncovering nuances that suggest the truth isn't either or, but when, where, and how catastrophes collided. The next time you hold a piece of petrified wood, remember, it's not just a rock, it's a puzzle box from a world in upheaval. The ground beneath our feet isn't as solid as we'd like to believe. In seconds, an earthquake can turn stable soil into liquid, topple skyscrapers, and even tilt the landscape itself, leaving entire forests leaning like drunks after last call. This isn't hypothetical. During the 2011 Tohoku earthquake in Japan, the seafloor off the coast shifted by a staggering 50 meters in moments. On land, trees near the epicenter tilted en masse as the soil liquefied beneath them, their roots suddenly suspended in what amounted to watery quicksand. Now imagine that same force applied to the ancient forests we find fossilized at bizarre angles across the globe. Could tectonic violence, the sudden lurching of continents, be the hidden hand behind these petrified snapshots of chaos? Paleoseismologist Dr. Raj Patel studies seismites, rock layers twisted and fractured by ancient quakes, and he's found them in close association with tilted fossil forests from Patagonia to Mongolia. These seismites aren't just cracks, they're signatures of catastrophe, showing where the Earth convulsed with enough force to deform stone. In some cases, the layers above and below these disturbed zones are perfectly flat, suggesting the quake struck suddenly, rearranged everything, and then stopped, leaving the landscape frozen in its new, disheveled state. It's the geological equivalent of a burglar who flips your couch but leaves the rest of the room untouched. The mechanics are terrifyingly simple. When a major quake strikes, seismic waves ripple through the ground like cracks in a windshield. In waterlogged soils, these vibrations can liquefy sediment, transforming solid earth into a slurry that swallows trees whole. But here's the kicker. If that slurry is then buried rapidly, say by a landslide or flood, the trees can fossilize in their tilted positions, their roots preserved mid-collapse. Chile's 2010 earthquake offers a modern parallel. Near the epicenter, entire groves of trees sank into the ground, some at 20-degree angles as the sediment beneath them turned to soup. If those trees were buried by the subsequent tsunami's sediment, they'd look eerily similar to the fossil forests we find today. Yet earthquakes don't just knock trees over, they can literally change the tilt of the land. Satellite data from Nepal's 2015 quake showed entire regions uplifted or depressed by meters, altering the angle of hillsides overnight. Apply that to an ancient forest growing on a fault line, and you've got a recipe for instant fossilization. Trees that once grew vertically suddenly find their roots on a slope, their trunks leaning like the Tower of Pisa. If mineral-rich waters then seep in, preserving them before decay can set in, you're left with a petrified forest frozen mid-fall. The smoking gun. Fossilized forests often cluster near known tectonic boundaries. The tilted trees of Scotland's Fossil Grove, for example, sit atop the Highland Boundary Fault, where ancient quakes could have jolted the ground like a tablecloth yanked from under a dinner setting. Even more telling, some sites show trees tilted in opposing directions, some northeast, others southwest, as if the ground itself was warping beneath them. Dr. Patel calls these seismic compasses, their angles hinting at the direction of long-vanished tremors. But the most haunting evidence comes from trees that didn't just tilt, they twisted. In New Zealand's Curio Bay, fossilized conifers show spiral fractures in their trunks, the kind of damage caused not by steady pressure, but by sudden torque. Picture a giant wrench gripping the earth and giving it a violent twist. That's the power tectonics can unleash, and when it happens, it doesn't just leave scars on the land. It etches them into stone, turning forests into monuments of planetary violence. Mainstream geology paints a comfortable picture of our planet's past, one where climate shifts unfold over millennia, glaciers advance and retreat like slow breaths, and forests gradually give way to changing conditions. But the fossil record keeps whispering a different story. Those petrified trees frozen mid-sway, their leaves still clinging to branches, their roots gripping soil that turned to stone beneath them. They don't speak of gradual change. They scream of catastrophe. Take the Younger Dryas period, roughly 12,000 years ago, when Earth's temperatures plummeted in a geological blink. Ice core records show this wasn't a gentle cooling. It was a planetary fever breaking overnight, with some estimates suggesting temperatures dropped by up to 15 degrees Fahrenheit in just a decade. Mammoths flash frozen with tropical plants in their stomachs, entire ecosystems uprooted and buried beneath this chaos, fossilized forests preserved so perfectly they might as well be botanical crime scenes. The controversy lies in what triggered such abrupt shifts. One camp points to the heavens specifically, comet fragments theorized to have struck the ice sheets of North America. The impact hypothesis suggests these cosmic bullets could have vaporized glaciers in an instant, sending torrents of meltwater into the oceans and disrupting global currents. The result, a climate roller coaster, floods drowning coastal forests, then freezing winds locking them in permafrost before decay could begin. Evidence like nanodiamonds and platinum spikes in sediment layers lends credence to this idea, though skeptics argue these markers could have earthly origins. Others blame volcanic winters. When Indonesia's Mount Toba erupted 74,000 years ago, it spewed enough sulfur dioxide to block sunlight for years, triggering a volcanic winter that may have decimated early human populations. Similar eruptions could explain fossil forests buried under ash layers hundreds of miles from any known volcano. The catch: volcanic winters typically unfold over years, not days too slow to account for trees fossilized with their foliage intact. Unless, of course, the eruptions coincided with other disasters, like methane releases from thawing permafrost, creating a domino effect of cooling and flooding. Then there's the wild card: rapid polar shifts. Paleomagnetic data shows Earth's magnetic poles have wandered and occasionally flipped over eons, some researchers, like geophysicist Dr. Elise Carter, proposed that if the crust shifted suddenly due to imbalances in ice distribution or mantle dynamics, it could have relocated entire climate zones in a matter of months. Forests accustomed to temperate weather might suddenly find themselves in Arctic darkness, their cells freezing before they could even wilt. This could explain why Antarctic fossil forests contain tree rings showing no signs of seasonal stress. They were growing steadily until catastrophe struck. The implications ripple beyond academic debate. If climate can turn on a dime, then today's gradualist models might be missing a critical piece of the puzzle. Modern coral reefs bleaching in warming oceans, boreal forests succumbing to beetle infestations. Are these slow declines or the first tremors of a system primed for sudden collapse? Fossilized forests don't just offer clues about the past, they're warning signs written in stone. When trees standing tall one day are stone the next, it's a reminder that nature doesn't always move at the pace we find comforting. Sometimes it jumps. Antarctica wasn't always this frozen wasteland of howling winds and endless ice. Peel back the layers of time, and you'd find a continent draped in lush forests, their leaves whispering in temperate breezes. A world so alien to today's Antarctica, it might as well be another planet. But here's where it gets eerie. These ancient trees didn't just die and decay. They were frozen in time with such precision that scientists can count individual cell walls under a microscope, as if someone hit pause on their biology mid-growth. The most baffling specimens come from the transantarctic mountains, where fossilized tree trunks still stand upright, their roots gripping soil that turned to stone. These aren't the skeletal remains of slow decay, they're snapshots of sudden catastrophe. Geologist Dr. Emily Wang describes them as botanical Pompeii, preserved so perfectly that some still have their bark, their branches, even their leaves attached. This level of detail doesn't happen over centuries, it demands near instantaneous freezing, a climate plunge so rapid that decay couldn't even begin. So what could flip Antarctica's switch from greenhouse to icebox so abruptly? One theory points to glacial surges. Imagine ice sheets advancing not over millennia, but in months, burying entire forests under crushing weight before bacteria could break them down. Modern glaciers can move startlingly fast. Alaska's Black Rapids Glacier once surged 100 times its normal speed, covering miles in months. Scale that up to continent-sized ice sheets, and you've got a recipe for flash fossilization. But there's a wilder possibility: polar wander. Earth's poles aren't fixed. Magnetic records show they've migrated and sometimes flipped over eons. Some researchers propose that Antarctica's drastic cooling came from the continent itself shifting position, drifting into the polar zone where endless winter took hold. If true, these fossilized forests might capture the moment Antarctica crossed a climatic tipping point, their cells freezing mid-photosynthesis as the sun vanished for months at a time. The smoking gun, tree rings. Many Antarctic fossils show no signs of seasonal stress, no narrowing rings from harsh winters, no insect damage. These trees were growing steadily, healthily, right up until disaster struck. It's as if they were living in perpetual spring before being plunged into deep freeze. Even more telling, some specimens contain fossilized pollen from plants that couldn't survive polar darkness, proving Antarctica's forests thrived under milder skies before catastrophe rewrote their fate. What does this mean for us today? These icy time capsules prove climates don't always change gradually. Sometimes they collapse like a house of cards. As we watch modern ice sheets destabilize and ocean currents wobble, Antarctica's fossilized forests stand as silent sentinels, reminding us that planetary equilibrium is fragile and that tomorrow's climate might not resemble yesterday's in ways we're only beginning to understand. Radiocarbon dating is supposed to be science's timekeeper, a precise clock measuring the age of ancient materials. But when it comes to fossilized forests, this clock seems to be telling conflicting stories. Take the famous Axel Heiberg Island fossil forests in the Canadian Arctic, where petrified wood samples from the same layer have returned dates varying by thousands of years. Some logs appear startlingly young compared to the rock strata encasing them, as if the trees grew long after the surrounding stone formed, a geological impossibility. The mainstream explanation points to contamination. Groundwater percolating through porous petrified wood can deposit younger carbon, skewing results. Modern root systems invading ancient specimens or bacterial activity introducing fresh organic material might also distort readings. Dr. Lisa Yong, a radiocarbon dating specialist, compares it to finding a smartphone in a medieval castle. It doesn't mean the castle was built yesterday. Her team has demonstrated how even microscopic fungal growth inside fossilized cells can shave millennia off apparent ages. Yet alternative researchers highlight anomalies that contamination can't easily explain. In Yellowstone's Specimen Ridge, some vertically stacked fossil trees show inverted dates, the upper layers dating older than those beneath them, like finding a buried skyscraper where the penthouse was built before the foundation. Then there's the young wood phenomenon, where inner tree rings date younger than outer rings, reversing the natural growth sequence. Paleobotanist Dr. Henry Cowan proposes these paradoxes might reflect a carbon reset event, a global catastrophe that temporarily scrambled atmospheric carbon ratios. Imagine a volcanic winter or comet impact so devastating it choked the skies with ash, stalling photosynthesis worldwide. Plants absorbing this abnormal air could record skewed carbon signatures, making them appear artificially young when dated millennia later. The Younger Dryas period, with its abrupt climate shifts and suspected extraterrestrial impacts, becomes a prime suspect. If such an event occurred, standard calibration models would misfire, like trying to decode a scrambled radio transmission. The debate reaches its peak with living fossils, petrified wood yielding radiocarbon dates implying they were alive just thousands of years ago, not millions. Mainstream labs often dismiss these as contamination errors, but independent researchers like Dr. Elena Petrova counter that the patterns are too consistent to ignore. Her studies of Siberian permafrost preserved wood show similar age discrepancies clustered around known extinction events, hinting at moments when Earth's carbon cycle went haywire. What's at stake isn't just academic, it's our fundamental understanding of geological time. If these dating anomalies reflect real events rather than measurement noise, they suggest our planet's history includes chapters of sudden, catastrophic change that current models struggle to explain. Like detectives finding fingerprints that don't match any suspect, scientists are left questioning whether the fault lies in their tools or in their assumptions about how time is recorded in stone. Humanity's oldest stories whisper of water torrents that swallowed mountains, waves that purged civilizations, floods so vast they reset the world. The Epic of Gilgamesh, inscribed on clay tablets 4,000 years ago, describes a deluge where the gods regretted making mankind. The Hindu Puranas speak of Matsya, the fish god who saved humanity from a cosmic flood. And of course, there's Noah's Ark, the biblical tale where rain fell for 40 days and 40 nights, wiping the slate clean. These aren't just isolated myths, they're a global chorus of catastrophe, echoing across hundreds of cultures from the Aztecs to the Aboriginal Australians. Now, imagine standing in one of those petrified forests. We've been exploring trees frozen upright, their roots tangled in stone, their branches snapped as if by some unimaginable force. For some, these silent witnesses aren't just geological curiosities. They're physical proof that the flood myths were real. Creationist groups have long pointed to Polystrate fossils, those trees piercing multiple rock layers, as evidence of a single, catastrophic burial consistent with a worldwide flood. They argue that slow sedimentation over millions of years couldn't preserve trees so perfectly, and that the sheer scale of these fossilized forests demands a disaster of biblical proportions. Mainstream science pushes back hard. Geologists like Dr. Sarah Whitmore emphasize that while megafloods certainly occurred, like the Missoula floods that scoured Washington state with walls of water taller than the Space Needle, they were regional events, not planet-wide. The fossil record shows forests buried at different times across millennia, not simultaneously in one grand cataclysm. And then there's the radiocarbon dating we discussed earlier, which places many fossilized forests far outside the timeline suggested by literal readings of flood myths. But here's where it gets fascinating. Even skeptical researchers admit that ancient stories often contain kernels of truth. Historian Dr. Liam O'Connor studies how oral traditions preserve real events across generations. Take the Aboriginal stories of Australia's coastline, he explains. For years, scientists dismissed tales of lands submerged by rising seas as allegory, until underwater archaeology proved these oral histories accurately described coastal changes from the end of the last ice age. Similarly, the Greek myth of Atlantis may exaggerate, but it could encode memories of the Thera eruption that devastated Bronze Age Crete. Could fossilized forests be another example of this phenomenon? Consider the Pacific Northwest's ghost forests, stands of drowned cedars killed when tectonic shifts suddenly lowered the coastline, allowing salt water to invade freshwater ecosystems. These events, occurring around the year 1700, were recorded by indigenous oral histories long before modern science confirmed them. Now imagine that same process on a continental scale during the meltwater pulses of the last ice age, when rising seas could have submerged entire forests in years, not centuries. The resulting tales, passed down through generations, might well evolve into legends of world-ending floods. The middle ground might be this: while there's no evidence for a single global deluge, our planet has endured countless localized cataclysms, volcanic eruptions, glacial outbursts, tsunamis, that could inspire flood myths. Fossilized forests, with their snapshots of sudden burial, remind us that these disasters weren't just stories. They were real events seared into cultural memory. Whether through the lens of faith or science, one truth emerges: humanity has always lived on a planet capable of radical, violent change, and the trees turned to stone are its most haunting witnesses. Mount St. Helens was sleeping peacefully on the morning of May 18, 1980, until it wasn't. In seconds, the mountain's north face collapsed, unleashing a landslide moving at 150 miles per hour. Behind it came a lateral blast of superheated gas and rock, leveling 230 square miles of forest like a scythe through grass. But what happened next is what fascinates geologists. Spirit Lake became a time machine. The blast wave flung thousands of trees into the water, where many sank vertically, their heavy root balls dragging them downward until they stood on the lakebed like a phantom forest. Decades later, those logs are already mineralizing, their surfaces crusted with silica, nature's first steps toward petrification. This isn't just a disaster scene, it's a fossil forest in the making, playing out in fast forward before scientists' eyes. Across the Pacific, another modern tragedy offers equally striking parallels. When Japan's 2011 Tohoku earthquake triggered a tsunami, the waves didn't just carry away buildings, they ripped entire forests from the coastline. Satellite images later captured something astonishing: floating islands of debris, some spanning miles, with uprooted trees tangled in a chaotic embrace. Over months, these mats drifted across the ocean, their logs rubbing together, shedding bark, and slowly saturating with salt water. When they finally sank, some near the same trenches that birthed the earthquake, they settled into layers that future geologists might mistake for ancient cataclysms. Marine biologist Dr. Kenji Sato observes, "What we're seeing is the birth of potential polystrate fossils. If buried rapidly by sediment, these logs could one day pierce through rock layers just like their prehistoric counterparts." These aren't isolated case studies. In Iceland, the 2010 eruption of Eyjafjallajökull demonstrated how volcanic ash can preserve organic matter almost instantly. Farmers reported finding sheep carcasses buried in ash, their wool and skin intact, a macabre echo of Pompeii's human victims. Meanwhile, in the Amazon, seasonal floods routinely submerge vast stretches of forest, with trees surviving underwater for months. While most eventually decay, those trapped in oxygen-poor, sediment-heavy channels could fossilize under the right conditions. Hydrologist Dr. Amanda Ribeiro notes, "We're watching nature experiment with fossilization in real time." The recipe's simple: take a living ecosystem, add catastrophe, and bury rapidly. The ingredients haven't changed in millions of years. The lesson from these modern disasters is clear: fossilization doesn't demand eons. Given the right upheaval, it can happen in days. When Mount St. Helens erupted, it didn't just kill trees, it created a laboratory for petrification. The heat sterilized organic material, slowing decay. The ash provided silica-rich minerals. The landslides buried everything under airtight sediment. It's as if the mountain staged a reenactment of prehistoric catastrophes, complete with special effects. And just like their ancient counterparts, these modern fossils in progress come with quirks. Some Spirit Lake logs float vertically for years before sinking, mimicking the upright stumps of Yellowstone. Others drift horizontally, destined to become the horizontal specimens future paleontologists might puzzle over. What's revolutionary about studying these events isn't just confirming that rapid fossilization is possible, it's realizing how many ways it can happen. Tsunamis bury coastlines, volcanoes smother landscapes, earthquakes drown forests in liquefied soil. Each disaster writes its own signature into the fossil record. And when scientists compare these modern examples to ancient sites, the matches are uncanny. The jumbled logs of Japan's tsunami debris, they mirror fossil forests in Scotland. The ash-entombed trees of Iceland, dead ringers for Wyoming's petrified stands. Even the Amazon's drowned forests hint at how coal seams might form, not over millennia, but in sudden, waterlogged pulses. Disaster researcher Dr. Sophia Kim puts it bluntly, "We used to assume the past was a quieter place. Now we know better. Every time a modern catastrophe fossilizes a forest, it's like receiving a postcard from deep time, one that reads, 'Wish you were here.'" It's chaos, and as climate change increases the frequency of megafloods, wildfires, and extreme weather, we may be creating more fossil forests than we realize. Future geologists studying our era might find petrified trees snapped by hurricanes or charred by wildfires before mineral-rich floodwaters sealed them in stone. The Earth hasn't stopped writing its violent diary, we're just beginning to understand the language. Permineralization is nature's alchemy, a process so precise it turns fragile wood into enduring stone, molecule by molecule. Picture a sponge soaking up water, except instead of water, it's silica-rich solutions seeping into every cell of a fallen tree. Over time, those minerals crystallize, replicating the tree's structure with such fidelity that under a microscope, you can still see the ghostly outlines of individual cell walls. But here's the catch: timing is everything. Too slow and decay wins, leaving behind only a hollow impression. Too fast, and the minerals overwhelm the delicate cellular architecture, collapsing it into a featureless lump. The fossilized forests we've been exploring, those upright stumps in Yellowstone, the tilted giants of Antarctica, are testimony to a perfect storm of conditions. They weren't just buried, they were bathed in mineral-rich waters that flooded their tissues at just the right speed. Think of it like pouring plaster into a mold, too leisurely, and the mold degrades before the plaster sets, too hastily, and the plaster clumps unevenly. These forests hit the sweet spot, preserving bark texture so finely you can still trace the grooves where beetles once burrowed. What's fascinating is the chemistry behind this. Silica, often dissolved in groundwater from volcanic ash, is a common player. When it infiltrates wood, it bonds with organic compounds, gradually replacing them while maintaining the original structure. Calcite, another frequent accomplice, works similarly but leaves fossils with a creamy, marble-like sheen. The key is concentration too dilute, and the minerals can't outpace decay, too concentrated, and they clog the wood's pores like concrete in a drain. Fossilized forests suggest environments where mineral saturation was just right, likely due to catastrophic events. Volcanic eruptions, for instance, could have dumped ash into waterways, turning rivers into silica soups that engulfed forests. Floods might have carried dissolved minerals from distant sedimentary basins, saturating submerged trees before decay could begin. Modern examples prove how quickly this can happen. In New Zealand's hot springs, researchers have observed wood silicifiing in mere decades, not millennia. The water, supercharged with silica from geothermal activity, permeates logs so thoroughly that their growth rings remain visible even as they turn to stone. Similarly, in Iceland's steaming vents, birch branches have been found partially petrified after just a few years. These cases mirror the Goldilocks conditions of ancient fossil forests, where disaster created a mineral-rich rush job. But permineralization isn't just about chemistry, it's a race against time. For a tree to fossilize this way, decay must be stalled before it starts. That's why the most pristine specimens are often linked to oxygen-poor environments, deep water, airtight ash layers, or boggy swamps where bacteria struggle to break down wood. It's no coincidence that many fossil forests are found in areas that once experienced sudden inundation or burial. The trees didn't just die, they were entombed in conditions that pressed pause on decomposition long enough for minerals to work their magic. The implications stretch beyond curiosity. By studying these processes, scientists can identify ancient disaster zones, places where floods, eruptions, or quakes created the perfect storm for preservation. And when they find fossilized wood with cellular details intact, it's a clue that the past wasn't always the slow, patient crawl we imagine. Sometimes it was a sprint, with minerals and catastrophe collaborating to turn living forests into stone before they could even fall. The fossilized forests standing sentinel across our planet aren't just relics of individual disasters, they're often tombstones for entire eras. Dig into the layers where these petrified giants lie, and you'll find something chilling. Many coincide with the darkest chapters in Earth's history, the mass extinctions that wiped out vast swaths of life. Take the end Permian event 252 million years ago, when 96% of marine species and 70% of terrestrial vertebrates vanished. In the rock record just before this biological apocalypse, there's a haunting pattern. Lush forests preserved in exquisite detail, their trunks frozen upright, their leaves still clinging to branches as if winter came overnight. Paleontologist Dr. Carlos Mendez calls them green graves, ecosystems fossilized mid-collapse by the same catastrophes that doomed countless species. The mechanics of this grim preservation are as brutal as they are precise. During the end Permian, Siberian traps volcanoes belched enough carbon dioxide and methane to spike global temperatures by 10 degrees Celsius in under 60,000 years, a geological blink. Acid rain scorched forests, while greenhouse gases turned oceans into lifeless soups. But here's the twist. Those volcanic eruptions also spewed silica-rich ash, which rained down on dying landscapes. As trees succumbed to the toxic atmosphere, mineral-laden floodwaters or ash flows buried them, sealing their final moments in stone. The result, fossil forests like those in Mongolia's Gobi Desert, where conifers stand petrified in growth position, their cellular structures intact down to the micron. These trees didn't just die, they were embalmed by the very forces that killed them. Asteroid impacts left similar calling cards. The Cretaceous-Paleogene boundary, marked by the Chicxulub impact 66 million years ago, contains a thin layer of iridium-rich clay, the asteroid's fingerprint. Just below it, in places like North Dakota's Hell Creek Formation, scientists have found log jams of fossilized trees tangled with dinosaur bones, all buried under sediment layers suggesting tsunami-like waves. The sequence reads like a disaster movie: impact, wildfires, mega tsunamis, then a global winter as dust blocked sunlight. Trees that survived the initial chaos likely froze in the ensuing darkness, only to be fossilized when sediment-laden floods swept across continents. But perhaps the most unsettling connection lies in methane. During the Paleocene-Eocene thermal maximum 56 million years ago, a massive methane release from seafloor deposits spiked global temperatures. In the Arctic's Ellesmere Island, fossil forests from this period show trees with bizarrely wide growth rings, evidence of a hyperactive growing season, followed by abrupt mineral staining in the wood. Researchers like Dr. Lin Wei suggest these trees absorbed toxic levels of metals from acidified soils before collapsing, their trunks preserved by methane-triggered landslides. What unites these scenarios is speed. Mass extinctions didn't just kill life, they reset the rules of preservation, creating conditions where entire forests could fossilize before decay took hold. And within these stone trees lie clues to recovery. Some fossil forests, like those in Australia's Sydney Basin, show pioneer species hardy plants that sprouted atop buried forests, signaling life's first tentative return. Others, like Antarctica's Permian fossils, reveal how ecosystems migrated poleward as climates grew hostile. These aren't just snapshots of death, they're time lapses of resilience, showing how Earth's green mantle regrew after devastation. The lesson: catastrophe isn't just destructive, it's a curator. The same forces that erase life can also immortalize it, turning forests into stone libraries where the planet's worst days are preserved alongside its first steps toward renewal. As we face our own era of climate upheaval, these ancient survivors whisper a dual truth. Life is fragile, but its capacity to rebound is written into the very rocks beneath our feet. Fossilized forests don't play favorites. They sprawl across every continent, from the steaming jungles of Indonesia to the frozen deserts of Antarctica. It's as if the planet once hosted a coordinated burial program for its trees, sealing them in stone from pole to pole. This isn't just a scattering of oddities. It's a planetary pattern, a chorus of catastrophe written in petrified wood. And that raises a haunting question. How could forests separated by oceans and climates meet the same fate, preserved with such eerie consistency? One camp points to the oceans specifically, the dramatic sea level swings of Earth's past. During ice ages, water locked in glaciers could drop sea levels by hundreds of feet, exposing continental shelves and creating vast, low-lying plains ripe for forest growth. When temperatures rose again, meltwater surges might have drowned these coastal forests en masse, submerging them in mineral-rich sediments. This could explain why fossil forests cluster in regions like the Arctic, where Canada's Axel Heiberg Island hosts mummified stumps that once grew at sea level before being flooded. But here's the catch: inland forests, like those in Arizona's Petrified Forest National Park, sit far from any ancient shoreline. If rising seas were the sole culprit, how did deserts and mountaintops get swept up in the fossil frenzy? Others blame atmospheric chaos. Imagine a sudden spike in carbon dioxide, say, from volcanic eruptions or methane releases triggering runaway global warming. In this scenario, extreme weather could become the great equalizer, with superstorms and floods ravaging forests worldwide. Paleoclimatologist Dr. Rajiv Kapoor cites the Paleocene-Eocene thermal maximum, a period 56 million years ago when temperatures spiked 8 degrees Celsius in under 20,000 years. That kind of shock doesn't just melt ice, he says. It rewrites rainfall patterns, intensifies monsoons, and turns stable landscapes into disaster zones overnight. Fossil forests from this era, like those in Germany's Messel Pit, show trees buried in deep lakes that might have swollen catastrophically under torrential rains. Yet there's a wild card in the deck: tectonics. When continents rift apart or collide, the resulting upheaval can trigger volcanic eruptions, earthquakes, and tsunamis on a hemispheric scale. The breakup of Pangaea, for instance, birthed the Atlantic Ocean while unleashing volcanic provinces that smothered millions of square miles in lava. Fossil forests from this era, like those in Patagonia's La Matilda Formation, often sit atop layers of basalt, their roots severed by flows that bake the soil beneath them. Geologist Dr. Hannah Lee wonders if these planetary-scale reorganizations created a perfect storm of instability, where forests worldwide faced burial by ash, lava, or floodwaters within mere centuries of each other. The sheer volume of sites defies coincidence. From New Zealand's Curio Bay to Egypt's petrified forests in the Sahara, the planet seems to have hosted a synchronized die-off or multiple pulses of it. Some layers even contain ghost forests stacked vertically, where successive stands of trees were buried in rapid succession. This isn't just disaster, it's disaster on replay. And that forces us to reconsider Earth's temperament. Modern geology often paints the past as a slow, methodical painter, but fossil forests suggest it could also wield a wrecking ball, reshaping continents in fits of violence. Perhaps the most unsettling implication is this: if rapid fossilization was once commonplace, maybe our planet's youth was far more turbulent than we've dared to imagine. Not a series of freak accidents, but a rhythm of upheaval, a world where forests grew with the knowledge that burial might come before decay. As Dr. Lee puts it, we're not just studying trees turned to stone. We're reading the diary of a planet that used to breathe fire, and that diary's pages are everywhere, waiting to tell us how thin the line between growth and fossilization really is. Long before microscopes or radiocarbon dating, our ancestors stumbled upon forests turned to stone, and their explanations were as colorful as the minerals staining the petrified wood. The Greeks, uncovering massive trunks on the island of Lesbos, spun tales of titans hurling stone trees during celestial battles. To them, these weren't fossils, they were the weapons of giants frozen mid-arc by Zeus's thunderbolts. Half a world away, the Navajo spoke of Yayat, so a monstrous being whose blood turned fallen trees to stone during epic battles with hero twins. These myths weren't just fanciful stories, they were early attempts to explain the unexplainable, to reconcile living forests with their stone doppelgangers. When European naturalists first encountered Arizona's petrified forest in the 1800s, they faced a different kind of dilemma. The upright stumps defied their understanding of geology. Charles Lyell, champion of gradualist theories, struggled to explain how entire forests could stand petrified without signs of slow sedimentation. His contemporaries proposed floods or volcanic eruptions, but even these ideas couldn't account for the sheer scale thousands of trees preserved across miles of desert. The confusion was so profound that some 19th-century scientists speculated these were not trees at all, but strange mineral formations mimicking organic shapes. Indigenous perspectives often came closer to the mark. The Lakota revered petrified wood as stone people, ancestors transformed by the Great Spirit during a primordial flood. Pacific Northwest tribes described forests that fled to the mountains during rising waters, turning to stone as the waves overtook them. These oral traditions, passed down through generations, encoded observations modern science would only later confirm, that sudden deluges could indeed entomb entire landscapes. The tension between myth and science reached its peak during the Bone Wars of the late 1800s, when rival paleontologists raced to catalog fossil sites across the American West. Petrified forests became battlegrounds not just for academic glory, but for competing worldviews. Some saw them as proof of biblical catastrophes, others as evidence of mundane processes stretched over eons. What none could deny was their power to disrupt assumptions. When railroad crews slicing through Wyoming's Badlands uncovered a petrified forest tilted at 30 degrees, even the most steadfast gradualists had to concede. These trees didn't lean, they were thrown. Today, we recognize these early encounters as milestones in a still unfolding mystery. Every culture that stumbled upon fossilized forests, from Chinese scholars documenting dragon bones in the Shanxi Basin to Incan priests interpreting petrified logs as messages from Pachamama, was grappling with the same fundamental question: how does life become stone? Their answers, whether mythic or mechanistic, reveal as much about human imagination as they do about Earth's capacity for transformation. The real magic lies not in the petrification itself, but in how these stone forests have compelled us, across centuries and civilizations, to keep rewriting the story of our planet. The secrets locked inside petrified wood are finally yielding to 21st century technology, revealing details our predecessors could only dream of glimpsing. Take CT scanning, a medical tool repurposed to act as geology's X-ray vision. At the University of Manchester, researchers recently scanned a 200-million-year-old conifer from Arizona's petrified forest, revealing not just growth rings, but the ghostly outlines of beetle larvae that tunneled through the living tree. These tiny passageways, narrower than a human hair, had been sealed in stone for eons, invisible to the naked eye. Now, they're evidence of an insect infestation frozen mid-feast, a snapshot of ecological drama preserved by catastrophe. Isotopic analysis is cracking open even deeper mysteries. By vaporizing microscopic samples with lasers, scientists can read the chemical fingerprints locked inside petrified wood. A study published last year in Geology analyzed oxygen isotopes in Antarctic fossil trees, uncovering a startling pattern. The trees drank water with a different isotopic signature than modern precipitation at those latitudes. The implication: Antarctica's climate was not just warmer in the past, its entire atmospheric circulation system operated differently, with rain patterns unlike anything we see today. These aren't just dead trees, they're ancient weather stations, they're stone cells recording millennia of climatic data. Then there's LIDAR, light detection and ranging, which is rewriting maps of prehistoric landscapes. In the Sahara's Tenere Desert, lasers penetrated meters of sand to reveal a lost forest of stone, its trunks still standing where dunes now drift. The images showed something astonishing. The trees were clustered around what appeared to be river channels, their roots tracing the outline of a vanished watershed. This wasn't just a forest buried by time. It was an entire ecosystem flash frozen by desertification. Its waterways erased so completely that only the petrified trees remembered their paths. Perhaps most revolutionary is the hunt for ancient biomolecules. While DNA typically degrades within thousands of years, some fossilized wood has yielded protein fragments and lipids molecular echoes of the tree's original chemistry. In Sweden's Siljan Ring, a meteorite impact crater, scientists found terpenes, organic compounds responsible for pine scent preserved in 380-million-year-old fossilized tree resin. The discovery suggests that under extreme conditions, even volatile organic molecules can outlast their creators by geological timescales. These tools are doing more than just confirming rapid burial, they're exposing patterns of planetary violence. CT scans of Yellowstone's upright fossil stumps show stress fractures consistent with sudden loading, as if tons of volcanic ash fell in days, not centuries. Isotopic analysis of Nova Scotia's Polystrate trees reveals saltwater signatures, hinting at tsunamis that drowned coastal forests. And LIDAR has mapped vast fossil graveyards in Patagonia where trees lie in parallel, all pointing downhill like matchsticks scattered by a flood's retreat. The most tantalizing revelations may lie ahead. Quantum diamond microscopy, a nascent technology, can detect weak magnetic fields in fossils, potentially revealing traces of Earth's magnetic polarity during extinction events. Meanwhile, AI algorithms are being trained to recognize patterns in fossilized wood that human eyes might miss, like subtle mineral variations signaling different burial phases. As these tools converge, they're painting a startling picture. Fossilized forests aren't just accidents of preservation. They're the archives of a planet that didn't always change gradually, sometimes it roared. And with every technological breakthrough, we're learning to listen. Mainstream science offers compelling explanations for fossilized forests, volcanic eruptions, megafloods, earthquakes. But venture beyond the established theories, and you'll find ideas so radical they rewrite the rules of geology itself. Take Earth crust displacement, a hypothesis that sounds ripped from a sci-fi novel. Proposed in the mid-20th century by scholar Charles Hapgood, it suggests the planet's outer shell can and has shifted catastrophically, like the skin of an orange sliding over its pulp. Imagine continents lurching thousands of miles in days, poles careening into new positions, and forests that once basked in temperate sunlight suddenly plunged into polar darkness. For supporters of this theory, Antarctica's fossilized forests aren't just relics of a warmer past, they are evidence the continent itself wasn't always at the South Pole. Frozen in place by a sudden crustal shift, these trees wouldn't have had time to wither. They'd simply stop mid-photosynthesis as their world tilted beneath them. Then there's the plasma discharge theory, championed by physicists like Dr. Paul Allen. Picture cosmic lightning bolts, not the tame forks we see during storms, but planet-scorching arcs of energy powerful enough to flash-bake entire landscapes. Allen's research points to strange features found near some fossil forests: vitrified soil, twisted rock formations, and magnetic anomalies that defy conventional explanations. His controversial proposal that millennia ago, Earth passed through a region of intense electromagnetic turbulence, perhaps during a solar micronova or interstellar plasma storm. Trees caught in these discharges wouldn't just burn, they'd undergo instant mineralization, their organic matter replaced by stone in seconds under the onslaught of charged particles. It's a fringe idea, but one that gains eerie traction when you examine sites like Arizona's petrified forest, where some logs show glass-like fusion crusts alongside their typical silicification. These theories might reside on science's outer edges, but they share a provocative thread: the acknowledgement that our planet's history could include events so extreme they've been scrubbed from conventional models. Geologist Dr. Miriam Chen, who specializes in catastrophic geology, puts it bluntly: we've never witnessed a supervolcanic eruption or a Chicxulub-scale impact in human history. Who's to say even wilder phenomena aren't possible? She cites the Younger Dryas period's abrupt climate swings still not fully explained, as proof that Earth systems can pivot violently under the right triggers. What makes these ideas compelling isn't just their audacity, but the questions they force us to confront. If Earth's crust has shifted suddenly before, could it happen again? Could forces beyond our atmosphere, solar flares, gamma-ray bursts leave their own fossilized signatures? The very existence of these debates underscores a humbling truth. For all our advances, the planet still holds mysteries that defy textbook explanations. Fossilized forests, with their surreal preservation, act as Rorschach tests for science. Some see gradual processes punctuated by disaster. Others see fingerprints of planetary chaos we've yet to fully imagine. Both perspectives agree on one thing: these stone trees are more than relics. They're invitations to rethink everything we assume about Earth's past and its capacity for sudden, spectacular change. Fossilized forests are more than just geological oddities, they're time capsules of resilience, capturing moments when life faced the unimaginable and found a way forward. Beneath the layers of stone and sediment, these ancient ecosystems hold blueprints for survival, written in the language of growth rings and root systems. Take the fossilized forests of Yellowstone, where layers of upright stumps aren't just records of destruction, they're testaments to rebirth. Between some of these layers, scientists have found delicate root networks of young trees, their fragile tendrils reaching into the ash that buried their predecessors. These saplings didn't wait for perfect conditions. They seized the first opportunity to grow, turning disaster into fertile ground. Ecologist Dr. Rachel Green describes these sites as nature's contingency plans, where life's persistence defies even the most catastrophic odds. In Patagonia's La Matilda Formation, fossilized tree trunks stand alongside the remains of fern fronds and fungi, a snapshot of an ecosystem already rebuilding. The fungi are particularly telling. These organisms specialize in breaking down dead matter, recycling nutrients to fuel new growth. Their presence signals not just survival, but renewal, as if the forest was already composting its own collapse to feed its comeback. It's a pattern repeated across the globe. In Mongolia's Gobi Desert, petrified logs are encased in layers of coal, evidence that later forests thrived so densely their remains became fuel for future civilizations. But resilience isn't just about bouncing back, it's about adaptation. Fossilized forests near the Arctic Circle reveal trees with unusually wide growth rings, a sign they flourished in warmer climates before their world chilled. Yet when temperatures dropped, some species didn't just die out, they evolved. Conifers developed thicker bark to insulate against cold, while deciduous trees shed leaves to conserve energy. These adjustments are etched into the stone, growth ring by growth ring, showing how life tweaks its strategies in response to shifting rules. Dr. Green notes, these trees didn't have the luxury of time to adapt. Their fossils show us evolution on fast forward, with the stakes set to extinction or survival. The parallels to today's climate crisis are impossible to ignore. As modern forests face rising temperatures, wildfires, and invasive species, the fossil record offers both warning and wisdom. The buried forests of Antarctica, for instance, reveal what happens when ecosystems hit tipping points, flourishing one era, frozen the next. Yet they also demonstrate life's stubborn tenacity. In Scotland's Fossil Grove, a layer of fossilized moss carpets the petrified stumps, proof that even after catastrophe, the smallest and humblest organisms can pave the way for recovery. Perhaps the most profound lesson lies in the diversity of responses. Some fossil forests show monoculture stands of a single tree species that dominated until disaster wiped them out. Others, like the mixed conifer and fern assemblages found in Nevada's Berlin Ichthyos or State Park, reveal ecosystems where biodiversity acted as a buffer, ensuring that even if one species faltered, others could fill the gaps. This dichotomy mirrors modern debates about reforestation. Should we plant resilient monocultures for quick recovery, or prioritize diverse ecosystems that might withstand unpredictable shocks? The stones, it seems, suggest the latter. What emerges from these ancient testimonies isn't just a story of survival, but a manifesto for improvisation. Fossilized forests didn't rebuild as perfect replicas of what came before. They reinvented themselves, seizing new niches, testing new strategies. As climate change accelerates, their message is clear: resilience isn't about returning to normal. It's about rewriting the rules and doing so with the urgency of a sapling breaking through ash. Petrified wood doesn't just belong to geologists, it's become a global commodity, carved into coffee tables, polished into pendants, and even ground into pigment for high-end paints. Walk through any gem and mineral show, and you'll find vendors hawking slices of ancient trees like fine art, their vibrant silica swirls fetching hundreds per slab. The trade isn't new. Victorian elites coveted petrified wood as cabinet curios, and Tiffany & Co. once crafted brooches from Arizona's rainbow-hued specimens. But today's market operates at an industrial scale, with online auctions offering fossilized logs the size of cars to the highest bidder. This commercial frenzy puts parks like Arizona's petrified forest in an impossible position. Rangers there confiscate thousands of stolen fragments annually, some smuggled out in suitcases, others mailed home by tourists who couldn't resist a souvenir. The theft isn't trivial. Each piece is a lost data point, a missing clue in Earth's climatic archive. Infrared cameras and weight-sensitive trails now monitor vulnerable areas, while signs warn visitors that taking even a pebble could cost $20,000 in fines. Yet the allure persists. As one ranger noted, people see these stones as dead things, not scientific records. They don't realize they're pocketing pages from our planet's diary. The ethics grow murkier where trade is legal. Madagascar's petrified Araucaria wood, streaked with cobalt blues and crimsons, is mined legally but often under grueling conditions, with laborers paid pennies to extract fossils that sell for thousands overseas. In Indonesia, entire fossilized logs are chainsawed into slabs for export. Their growth rings once a climate record reduced to decor. Even regulated markets have unintended consequences. When private collectors buy rare specimens for display, those pieces vanish from scientific scrutiny. Paleobotanist Dr. Elena Torres recounts a case where a collector's polished table slab held the only known example of a prehistoric beetle species, its outline preserved in the wood but now trapped behind glass in a penthouse. Yet banning all commerce isn't the answer. For some communities, fossil sales are vital income. Namibia's Petrified Forest National Monument funds conservation through limited, licensed sales of fallen wood. And public access matters. Handling petrified wood sparks curiosity that textbooks can't match. The challenge lies in balancing these needs. Some propose a certification system, like the Kimberley process for diamonds, tracing ethical sourcing from ground to buyer. Others advocate for 3D scanning, letting museums share digital replicas while originals stay protected. The deeper question lingers: can we appreciate Earth's history without consuming it? Maybe the answer lies in Japan's Satoyama philosophy, finding harmony between use and preservation. After all, these stone trees survived asteroids and volcanoes. Whether they survive human fascination may depend on our ability to value them as more than just pretty rocks. Beneath Antarctica's ice sheets, drills are piercing thousands of feet into frozen darkness, not just hunting for climate data, but for entire lost worlds. In 2023, a team from the University of Cambridge pulled up a sediment core containing something extraordinary: fragments of fossilized roots and pollen from a forest that thrived just 900 miles from the South Pole. These weren't scattered twigs, but remnants of a lush ecosystem buried under ice for millions of years. The discovery sent shockwaves through the scientific community, not just for what it revealed about Antarctica's green past, but for how it was found. Using radar scans from satellites, researchers had mapped ghost landscapes beneath the ice-ancient river valleys and basins where forests once grew. Now, targeted drilling is turning those ghostly outlines into tangible evidence, one core sample at a time. Meanwhile, in the Amazon, satellites equipped with LiDAR are revealing a different kind of secret. Beneath the rainforest's dense canopy, laser pulses have detected strange geometric patterns, not just the expected ruins of human civilizations, but vast tracts of petrified wood protruding from riverbanks. These fossil forests, invisible to the naked eye under layers of vegetation, suggest the Amazon wasn't always the unbroken jungle we know. Some specimens show fire scars and abrupt mineral staining, hinting at catastrophic floods or droughts that flash-preserved entire stands of trees. Brazilian geologist Dr. Luisa Mendes describes them as time capsules wrapped in green, waiting for technology to peel back the layers. But perhaps the most surreal explorations are happening underwater. Off the coast of Wales, marine archaeologists recently stumbled upon a submerged forest dating back to the last ice age, its oak and pine trunks still rooted in what was once dry land. As sea levels rose, these trees were swallowed by the ocean, only to be preserved in the oxygen-poor depths. Similar sites are emerging worldwide, from Doggerland, the drowned hunting grounds of prehistoric Europe, to Indonesia's Sunderland, where divers have found mangrove forests petrified in saltwater. These underwater graveyards aren't just curiosities, they're proving grounds for new fossilization theories. Marine geochemist Dr. Felix Wu notes that wood submerged in deep-sea brine pools can mineralize in decades, not millennia, a discovery that's rewriting the rulebook on how fast fossils can form. The tools of this hunt keep evolving. Hyperspectral imaging, originally developed for Mars rovers, is now being trained on fossil sites to detect mineral signatures invisible to human eyes. In Mongolia's Gobi Desert, this technology recently identified a hidden trove of petrified conifers by spotting their unique silica fingerprints under layers of sandstone. Even AI is joining the search, with machine learning algorithms scouring satellite images for subtle terrain anomalies that might signal buried forests. One such program, developed at Stanford, flagged a site in Patagonia that turned out to contain hundreds of tilted fossil trees, all aligned as if felled by the same ancient tsunami. What unites these disparate efforts is a growing realization. We've been looking for fossil forests in all the wrong places. Traditional searches focused on arid badlands and exposed cliffs, but the next frontier lies under ice, water, and jungle. And with every new discovery, the picture grows more complex. Last year, a diamond mine in Canada's Northwest Territories unearthed a fossil forest preserved at the Cretaceous-Paleogene boundary, the very layer marking the asteroid impact that killed the dinosaurs. The trees showed no signs of gradual extinction. They were frozen in growth position, their leaves intact, as if the sky itself had turned to stone that day. Explorer Dr. Mark Rivers puts it best: "We're not just filling gaps in the fossil record, we're finding chapters we didn't know existed." As technology peels back Earth's layers, these stone forests keep whispering the same urgent question: if so much has been hidden, what else might be waiting? The answers could rewrite not just the history of forests, but of our planet's capacity for reinvention. And somewhere, beneath ice or ocean or shifting sand, the next great revelation is already fossilizing, biding its time until we're ready to dig it up. Hollywood loves showing fossils forming over eons, a leaf slowly buried under layers of sediment, a dinosaur bone gradually turning to stone, but fossilized forests refuse to follow this script. Their trees stand upright, their leaves intact, their bark textures crisp, all screaming not of slow accumulation, but of sudden disaster. Take the petrified forests of Argentina's Santa Cruz province, where trees were buried so fast that some still have fossilized epiphytes clinging to their branches. These weren't leisurely burials, they were violent snapshots, nature hitting pause mid-catastrophe. Then there's the age assumption. Ask someone how old petrified wood is, and they'll likely say millions of years. Yet in New Zealand's hot water beach, hot springs have silicified tree trunks in less than 2,000 years, some still bearing Maori tool marks from when the wood was freshly cut. Even younger examples exist near Iceland's geothermal vents, where birch branches have partially petrified in mere decades. These aren't flukes, they're proof that under the right conditions, mineral-rich water, rapid burial, oxygen deprivation, fossilization can happen faster than a medieval cathedral takes to weather. The very word fossil trips people up. Derived from the Latin fossilis, meaning dug up, it carries no inherent age requirement. A mammoth bone frozen for 12,000 years is a fossil. So is a 19th century shipwreck's wooden hull already mineralizing in the Great Lakes. Preservation, not antiquity, is the key. This misunderstanding warps public perception, like assuming all fossils must be dinosaurs, when in reality most are far humbler: seeds, pollen, even bacteria. Perhaps the most persistent myth is that fossilized forests represent peaceful graveyards where trees grew, died, and were gently covered over time. The evidence tells a different story. In Washington's Ginkgo petrified forest, logs lie in chaotic jumbles, their branches snapped and trunks scarred by violent transport. At Scotland's fossil grove, trees stand tilted in unison like dominoes frozen mid-fall. These aren't orderly transitions from life to stone. They're botanical crime scenes where something interrupted the natural order, something big. Clarifying these misconceptions isn't just academic pedantry, it reshapes how we see Earth's history. If we imagine the past as exclusively slow and gradual, we miss the plot twists, the floods, eruptions, and impacts that rewrote landscapes overnight. Fossilized forests are nature's way of setting the record straight. Change isn't always patient. Sometimes it arrives like a thunderclap, leaving forests petrified not just in stone but in time. The fossilized forests we've explored aren't just relics, they're warnings etched in stone. As our planet's thermostat creeps upward, the same forces that flash-froze ancient ecosystems are stirring again, raising an unsettling question. Could modern forests face similar fates? The parallels emerge when you examine the triggers behind those prehistoric catastrophes: sudden methane releases, rapid sea level rise, volcanic winters, and compare them to today's climate crisis. Consider thawing permafrost. Across Siberia and Alaska, ground that's remained frozen for millennia is turning to sludge, releasing methane bubbles that ignite when touched with a match. These emissions mirror the Paleocene-Eocene thermal maximum 56 million years ago, when methane surges spiked global temperatures by 8 degrees Celsius. Back then, the resulting climate chaos left forests fossilized from Wyoming to Antarctica. Now, satellite data shows Arctic methane concentrations rising at alarming rates, with some plumes spanning miles. Glaciologist Dr. Nina Volkova notes, "We're watching the same dominoes line up, only this time human activity is knocking them over." Then there's the specter of rising seas. When ice sheets collapsed at the end of the last ice age, meltwater pulses drowned coastal forests so rapidly that cedars in Washington's Olympic Peninsula were preserved standing upright, their roots still gripping the soil when divers rediscovered them centuries later. Today, with Greenland and Antarctica shedding ice at unprecedented rates, scientists warn we could see similar inundations. Computer models suggest that if the Thwaites Doomsday Glacier collapses, a possibility within decades, it could raise global sea levels by 2 feet, submerging mangrove forests from Florida to Bangladesh. Unlike their ancient counterparts, these modern trees wouldn't fossilize instantly, but the principle remains. Stable ecosystems can unravel overnight when planetary conditions shift abruptly. Volcanic activity adds another layer of concern. While Yellowstone's supervolcano grabs headlines, smaller eruptions can still wreak havoc. The 2022 Hunga Tonga blast proved this, injecting enough water vapor into the stratosphere to temporarily warm the planet. On a larger scale, such eruptions could mimic the volcanic winters that buried forests during the Permian extinction, when sulfur aerosols blocked sunlight for years. Today, climate change may even increase volcanic risks. As Iceland's glaciers retreat, reduced pressure on magma chambers could trigger more frequent eruptions, a feedback loop with eerie echoes of the past. Yet the most immediate threat comes from compound disasters. Imagine a scenario where melting permafrost weakens Arctic slopes, triggering a landslide like Norway's 8,000-year-old Storegga slide. But this time, the collapse releases methane hydrates, accelerating warming, which in turn intensifies hurricanes that flatten coastal forests. Such cascades explain why Dr. Volkova calls fossilized forests stress tests for the planet, showing how interlinked systems fracture under pressure. The key difference this time: speed. Prehistoric climate shifts while rapid geologically unfolded over centuries. Modern warming is occurring 10 times faster than the Petam event, and humans, unlike ancient trees, can't migrate or adapt biologically at this pace. This acceleration means we're conducting an unprecedented experiment. Can industrialized civilization withstand changes that once turned forests to stone? While no one expects Manhattan to become a petrified forest, the mechanisms behind those ancient preservations, sudden burial, oxygen deprivation, mineral saturation, are finding modern equivalents. Wildfires so intense they sterilize soil, creating ash layers ripe for preservation. Floods carrying sediment loads 50% heavier than a century ago, thanks to erosion from deforestation. Even human-made time capsules like concrete jungles could one day fossilize, merging with nature's own record of this turbulent era. What fossilized forests ultimately teach us isn't doom, but perspective. They prove Earth systems have broken before and rebuilt differently, with life adapting in unexpected ways. The question isn't whether change will come, but whether we'll heed the stone-bound warnings of forests past, or become subjects of some future civilization's geological detective story. There's something hauntingly poetic about a forest turned to stone, a dissonance that sparks the creative mind like flint against steel. Artists have long been drawn to this collision of life and permanence, where time itself seems petrified. Salvador Dali's surrealist landscapes, with their melting clocks and barren trees, echo the twisted forms of Arizona's petrified forest, as if the rocks whispered their secrets to him in a dream. Georgia O'Keeffe, too, found inspiration in these skeletal remains, painting close-ups of fossilized wood so vivid they pulse with latent energy, the grain lines throbbing like veins. It's no accident that these artists fixated on petrified wood. Its very existence blurs the line between organic and inorganic, between what lives and what lasts, a paradox that fuels creativity. Literature, meanwhile, has weaponized fossil forests as portals to the uncanny. Jules Verne sent his characters tunneling through a subterranean forest of stone in Journey to the Center of the Earth, transforming geology into a stage for adventure. H.P. Lovecraft, ever the conjurer of cosmic dread, described ancient ruins at the Mountains of Madness where the very trees were stone, their branches frozen in silent screams. These weren't just set pieces, they were metaphors for humanity's insignificance against geological time. Even modern authors tap into this vein. In Jeff Vander Meer's Annihilation, the eerie, glassy trees of Area X owe a debt to real-life silicified forests, their unnatural shimmer a mirror for the story's themes of transformation and loss. Filmmakers, too, harness the unsettling power of petrified woods. The otherworldly landscapes of Annihilation and Avatar borrow their visual grammar from fossil sites, where towering stone trunks evoke alien worlds. But perhaps the most striking homage lies in Hayao Miyazaki's Nausicaa of the Valley of the Wind, where the toxic jungle's giant, crystalline fungi and petrified warrior statues feel ripped from a fossilized forest's playbook. These creations tap into a universal unease, the fear of being frozen in time, of life interrupted mid-motion. The allure extends beyond narrative to pure symbolism. Inuit carvers in Alaska craft intricate jewelry from petrified wood, seeing in its swirls the stories of ancestors turned to stone. Japanese gardeners incorporate fossilized logs into Kherson-Sui dry landscapes, where their textured surfaces represent mountains weathered by eons. Even tattoo artists ink petrified wood patterns onto skin, turning bodies into living monuments to resilience. What makes fossil forests such potent muses isn't just their strangeness, but their duality. They're both gravestones and time capsules, embodying destruction and preservation in one breath. For creators, they're a canvas for exploring mortality, how something as fleeting as a leaf can outlast civilizations when touched by catastrophe. They ask what will remain of us and how thin is the veil between life and stone. The answers, like the forests themselves, linger in that liminal space where science meets myth and where artists, like the minerals that petrified these trees, fill the voids with something enduring. Arizona's Petrified Forest National Park is like stepping onto an alien planet where the trees have turned to gemstones. Walk the Crystal Forest Trail, and you'll find logs splintered into segments that glow with quartz and amethyst hues, fractured by eons of erosion into nature's stained glass. But this isn't just a pretty rock show. Rangers here guide visitors to newspaper logs, specimens so finely preserved you can spot beetle trails etched into the bark like headlines from the late Triassic. Time your visit for sunrise when the low angle of the light sets the agatized wood on fire with reds and golds, and you'll understand why the Navajo called this place the place where the rainbow fell. For a Southern Hemisphere counterpart, Argentina's Petrified Forest National Monument in Patagonia offers a stark contrast. Here, the fossilized araucaria trees loom like monoliths, some measuring over 3 meters in diameter, relics of a time when this windswept steppe was a humid jungle. The magic lies in the details. Run your fingers over the trunk surfaces, and you'll feel the knobs and ridges of bark patterns unchanged for 200 million years. Local guides point out something extraordinary. Some logs are encrusted with opal, their cavities lined with fiery flashes of color where groundwater deposited silica over millennia. It's a reminder that fossilization isn't just preservation, it's alchemy. Scotland's fossil grove, hidden in a Glasgow park, delivers intimacy instead of grandeur. 11 upright stumps stand sheltered in a Victorian-era pavilion, their roots still gripping the carboniferous soil where swampy forests once thrived. Unlike the shattered logs of Arizona, these specimens are whole, their interiors hollowed out by time to reveal cross-sections of growth rings as precise as tree ring calendars. The real marvel, these trees fossilized not through catastrophe, but through gradual flooding, proof that nature's time machine works at multiple speeds. Touch the cool stone surface, and you're brushing against a snapshot from 330 million years ago, when Scotland straddled the equator. Museums worldwide are decoding these outdoor wonders for the curious. The Smithsonian's National Museum of Natural History displays a petrified log from Wyoming so massive it had to be lowered through the roof during construction. Slice it open, and you'll see rings documenting droughts and volcanic winters. Berlin's Museum für Naturkunde takes a different approach, with backlit thin sections of petrified wood that reveal cellular structures under magnification, turning fossils into stained glass windows of biological history. Even smaller institutions surprise. The Rice Northwest Museum of Rocks and Minerals in Oregon showcases petrified wood that fluoresces under UV light, its minerals glowing like neon signs from the Eocene. Technology is democratizing access like never before. Google Arts and Culture offers virtual dives into Namibia's petrified forest, where you can zoom in on fairy circles of stone logs arranged by ancient floods. The University of Texas's 3D Petrified Wood Repository lets you rotate specimens to study spiral fractures from prehistoric earthquakes, details often missed in glass museum cases. For educators, apps like Fossil Explorer overlay augmented reality forests onto classroom desks, letting students excavate layers with tablet screens. The true power of these encounters, whether physical or virtual, isn't just spectacle. Standing before a fossilized tree forces a reckoning with time's elasticity. These weren't abstract organisms in textbooks. They were living things that drank sunlight, weathered storms, and then, through planetary caprice, became something eternal. To walk among them is to have a conversation across epochs, where every mineralized knot and fracture tells two stories: how the tree lived and how the earth decided to freeze it in stone. The fossilized forests we've explored aren't just static museum pieces, they're time machines offering front-row seats to Earth's most dramatic turning points. Each petrified trunk, each tilted stump, each leaf preserved in stone tells a dual story, one of thriving ecosystems abruptly interrupted, and of a planet capable of radical transformation in the blink of geological time. Consider the haunting beauty of Yellowstone's upright giants, frozen mid-growth under volcanic ash, standing like sentinels from an age when fire rained from the sky. Or the Antarctic forests that now lie shattered across ice fields, their cells perfectly preserved despite millions of years of polar darkness. These aren't random anomalies, they're pages from a planetary diary written in silica and sediment. What makes these stone forests truly extraordinary isn't just their preservation, it's what they reveal about Earth's temperament. For too long, we've pictured geological change as a slow, steady march, like sand grains trickling through an hourglass. But fossilized forests shatter that illusion. They show us a world where continents can tilt overnight, where tsunamis can drown entire landscapes in hours, where volcanic winters can flash freeze ecosystems before the first leaf falls. Modern science is catching up to this reality, with satellite imaging and isotopic analysis confirming that many of these forests fossilized not over millennia, but in years or even days. The implications are profound. If Earth's past was shaped by both gradual processes and violent upheavals, then our understanding of planetary change needs rewriting. Perhaps the most urgent lesson lies in resilience. Many fossilized forests show signs of regrowth, young trees sprouting from the ashes of their buried ancestors, ferns unfurling in the shadow of tilted giants. This isn't just ancient history, it's a playbook for our climate future. As we face rising seas, supercharged storms, and ecosystem collapse, these stone time capsules remind us that life has weathered such shocks before. Not by staying the same, but by adapting sometimes in radical ways. The Araucaria trees of Patagonia's petrified forests, for instance, evolved thick bark to survive volcanic winters. Today's forests may need similar ingenuity to endure anthropogenic warming. Yet for all we've learned, the greatest revelation might be how much remains hidden. New technologies from quantum microscopes that read atomic-level mineral signatures to AI that reconstructs lost ecosystems from fossil fragments promise to unlock even deeper secrets. Already, researchers are finding chemical traces in petrified wood that could reveal ancient rainfall patterns, atmospheric composition, even the precise seasons when catastrophe struck. Each discovery peels back another layer, showing us a planet far more dynamic and far more unpredictable than we ever imagined. So the next time you hold a piece of petrified wood, remember, you're not just holding a rock. You're holding a moment suspended between life and stone, a split second when Earth's story took a sharp turn. These fossilized forests challenge us to think differently about time, about change, and about our own place in a world where stability is an illusion, and where the ground beneath our feet has rewritten its rules before. If you've enjoyed this deep dive into Earth's stone archives, I'd love to hear which discovery stunned you most. Was it the tsunami-toppled forests of Scotland? The opal-filled trunks of Argentina? Drop your thoughts below, and don't forget to follow for more journeys into our planet's hidden past. After all, the next great revelation might be buried just beneath our feet, waiting for its story to